Hello and welcome to a video on polar coordinates. Just so you know, the audio may sound slightly different today. I usually have a mic that's attached to my earbuds, which is closer to my mouth, so you might get some background noise, so I apologize for that. But we're going to start with the polar coordinate system today, understand why we would actually use that system, what's up with polar coordinates, and how that relates to rectangular coordinates. Now, just so you know, what I mean by rectangular coordinates, this is nothing new to you, it's just the way that it's said. So a rectangular coordinate is just a point on an xy plane or a Cartesian plane or a rectangular coordinate system. So 2, 5, 0, 0, 3, -1, something like that. But I'm going to start with defining what the polar coordinate system is by some of its components. And so I just want to point out here with this picture is we have this point called O. We could also think about it as 0. It's basically the origin. On Earth, O is considered to be the pole. So I'm going to write that down. So the North Pole or the South Pole. So if you could pretend being in space right now and looking down on Earth, you can see basically the Earth on its axis. Well, it doesn't look like it's on its axis because you just see a big sphere. And if that's the pole, then this ray emanating from the origin or from the pole is called the polar axis. You could think of the polar axis as being like a longitudinal line that emanates from the pole. So there are a bunch of these longitude lines on a globe that you wouldn't see when you look at the Earth, but when we map it out, all the longitudes go through each of the poles. And the main longitude, which is called the prime meridian, goes through Greenwich, England. And that's 0 degrees east or west. But in practical terms, the polar axis, as far as our calculators go, or when we sketch things on the coordinate plane or coordinate system, we could think of the polar axis as just like the x-axis. So in a polar coordinate system, there is no y-axis. The other piece to this puzzle here is that theta is in its normal location, which is basically inside of a triangle here. We don't usually sketch the triangle unless we're solving some sort of problem. And this point P, let me define this a little bit. There's this point P, we call it P, and in a polar coordinate system, we define that P by an R, which is like a radius, and theta. Okay, so that R is basically this distance from the pole to point P, and theta is the angle that's created by the polar axis and the ray emanating from the origin to point P. And one final thing, what is R? A little bit more about that. R is the directed distance from O to P. What that basically means is that R could be positive or negative. It's a directional piece. So that's just a little bit of background for the polar coordinate system, which makes a lot of sense because we live on a sphere. And so let's get a little bit more practical though. I hope you like my wonderful polar coordinate plane. What you see in front of you is a polar coordinate system along with a rectangular system. So you see the y-axis and the x-axis. So those aren't usually on the polar coordinate system. So I just want to help you see how we can plot point 2, pi over 3. So 2 is the radius, pi over 3 is, what is pi over 3? That is theta. So we could do one of two things. We could start with this point P and we could think the radius is 2. So we're going to go out to the second concentric circle and we have gone out 2 units. So we could be anywhere along this circle. Now the second piece, theta, tells us exactly where, the angle that we're creating with the point. So that pi over 3 is basically, here's pi over 6 and here's pi over 3-ish. So I could sketch like a ray from there. And so that point 2, pi over 3 is on this concentric circle where we created that ray. So there is point P. So I started with the 2 and I went to the pi over 3 angle. Now I could also just say, here's pi over 3, 60 degrees, and then I'm going to move to the second circle, and then I have my point. Let me show you a different one. Second one, Q, says 3 pi over 4, so let's create that angle first. Here's 1 pi over 4, 2 pi over 4. 3 pi over 4 is over here in quadrant 2. And if I were to move out 1, 2, 3, that would be a positive r. But a negative r would be in the opposite distance, or opposite direction is the word I'm looking for, opposite direction. So that would be right here. So here's 1, here's 2, here's 3, here's negative 1, negative 2, negative 3. So that point is called Q. Now another point we could call Q is 7 pi over 4, 1, 2, 3, 4, 5, 6, 7, and out 1 unit. So 1 comma 7 pi over 4. Let me show you 2 more, and I think you'll get the gist here. So R is going to be in the negative 45 degree direction. So here's negative 45, positive 45, negative 45. And we're going to move 3 units, so 1, 2, 3 units, and that is the R, big R. Not the best choice of letters, but that's fine. So once again, we're in the direction of negative 45 degrees, and we've moved out to the 3rd concentric circle. And then finally, in purple, 315 degrees. Let's count. Okay. 45, 90, 180, 270, plus another 45 is 315. Hey, wait a second. That's the same as R. So that's also T. So the last point just proves the fact that we could have multiple coordinates for the same point. That's not the case for a rectangular coordinate system. If I say 3 comma 5, there's only one location where 3 comma 5 is. It's x is 3, and then you go up to y equals 5. But because the polar coordinate system is based on a circle, you could do multiple rotations forward or backwards to get to the point that you're looking for. If you think about being a captain on a ship, I can give you multiple directional angles. I could say go in a 45 degree direction, or I could say go in a negative 360 plus 45 degree direction. We'll still get to the same spot. Or negative 45 and comma and 315 degrees, kind of like what I did here with these angles. All right, so that's polar coordinates, and now I'd like to just introduce you how to convert between coordinates. So just a little bit of a sidestep here. I just need to give you some equations here. There are 4 equations that we'll use to convert, and you're pretty much familiar with them. This is trigonometry at the core. Of course, we have a circle because trigonometry is based on circles and triangles, and we have all trig functions, all 3 of them defined here. You might want to note that the ones on the left are usually what you can use to convert from polar to rectangular, because we need an x and a y. And then the ones on the right are usually what we'll use to convert rectangular to polar. So those are 4 equations, 4 mathematical truths that will help us convert, but also understand equations a little bit later. That's topic 4b. So let's do both of those things. Let's go forward and backwards. Polar coordinates to rectangular coordinates first. First, let's understand what this point actually is. So on a coordinate plane, if we sketch, if we work with a bow tie and we sketch this triangle, 2 comma 7 pi over 6, so we're moving, here's 6 pi over 6, which is 1 pi, and then we're going to go 1 more pi over 6, which is 30 degrees. So you got a short triangle, or I guess not very tall down. So that theta inside there is 30 degrees. And if we just fill in some of our values here, this value is 2 because we've moved 2 units out. And it actually is consistent with the values of a basic right triangle. So this is negative root 3 here. So what I've done is I've basically already converted to rectangular. I have the point is we move to the left negative root 3 units and move down negative 1 units. So that's great and all, but what if we can't draw that picture as well as we can with a special triangle. We don't really need special angles. So the first thing that we'll do is we'll start with the x component, and we'll say that x is equal to r cosine theta. Now we could either use our calculators, or if we're working with exact values, just find out what cosine 7 pi over 6 is. And if we use our picture here, cosine of 7 pi over 6 is adjacent, negative root 3, over hypotenuse, 2. So we have 2 times negative root 3 over 2, which is, the 2's divide out, and we get negative root 3. Hey, not too bad. Now the only other piece is we're finding the y value, because there are 2 pieces to that. So we just do the same thing. We have sine 7 pi over 6, and we use the same picture. Using the picture over there, we look at sine, so sine is negative 1/2, and we have 2 times negative 1/2, which is negative 1. Now, in conclusion here, just notice that if we get a negative root 3 with cosine, we should be expecting a 1 in some sort of case, because it's a special right triangle. So those become the rectangular coordinates, negative root 3, comma, negative 1. Or if we were to write it in decimal, negative 1.73, comma, negative 1. Because there is a little method you could use your calculator for. TrigApps on a TI-84. Okay, that is polar to rectangular, and it's a very direct route to get to that. You could use the picture or the actual equations and use them both to confirm each other. Now let's go the other direction. Rectangular to polar, we have the point 1, negative 1, which is a rectangular coordinate. So notice how when I sketch my graphs, I'm purposely sketching them in a way that focuses in on the quadrant that I care about. So 1, negative 1. 1, negative 1. So again, I don't really need to sketch this triangle, but I'm doing it to help me understand what's going on. If I have a 1 and a negative 1, that means this is a root 2 based on the Pythagorean theorem, and that this is a 45-degree angle. But how can I prove that algebraically? That's what we're shooting for. So let's use the other formula, tangent theta. This is a mathematical truth here, is negative 1 over 1. So that means theta must be 45 degrees, or pi over 4. The best way to confirm that with a calculator, by the way, is to be in degree mode and punch that in second tangent of negative 1. So there we have it, done. That's our theta. Because what we're looking for is an r comma theta as a point. Now let's use the other equation, which is x squared plus y squared equals r squared. So here's x squared plus y squared equals r squared. That means r squared is 2, and r equals positive or negative root 2. Okay, we're wrapping things up here, and we have 2 answers for r, but we look at our picture over here, and we notice that if we're going in the direction of negative 45 degrees, that we must be going in a root 2 amount of distance. So that means we're choosing a positive r, root 2. And we're going in a negative 45 degree direction. Now if we wanted to use negative root 2, then we would go in a 3 pi over 4 direction. We would go up here to 3 pi over 4, but go backwards. We don't have to talk about that right now, but you'll experience some of that in some of your exercises. Alright, so what we just did is rectangular to polar, and we used these 2 equations here, but it just confirmed the picture that we already knew based on our trigonometric experience. Okay, hey, thanks so much for watching. I will leave you with this lovely picture. Take care.